but not a naked algebraic function like, I think I erased it, curses. I need another example to show you one that just has an algebraic function answer. Some of them do. Like if we look at 3/2 power in the denominator or something like that, it can just come out to an answer which is just an algebraic function. Yeah.
So using the hyperbolic trig function just makes it simpler than...
Yeah, because this is a horrible integral. This is maybe unfamiliar, but it's actually straightforward. I mean, you could convert this. You could just, instead of doing this integral, you could just do this integral, right? That's exponentials and a constant. You can always take an integral with cosh or power of cosh and just convert it to exponentials, and that you can integrate, right? If you're lost in how to do it hyperbolically. So you're like, well, do I need to know trigonometric substitution or hyperbolic substitutions? I think knowing both is healthiest because there are problems which are just easier in one world or the other. My default is to try the trig substitutions first, and then if I just run into something that's just awful, I'll try the hyperbolic version instead. Yeah.
Can we do an example with like higher powers? Like, are we going to see that on a test, like higher powers?
Yeah, I can look at an example with higher powers. Sure. In fact, what's that?
I was just going to say we can leave our answer in terms of hyperbolic or normal trig. Doesn't matter.
It depends on the question. Like I usually ask a question that says use a hyperbolic substitution to do this integral. But then I usually also have other questions on the test which are just free form, like just integrate. I might not even say trig substitution or hyperbolic substitution. I'll just say integrate this. It's up to you guys to go square root. I should be using one of my implicit substitutions to get rid of that root, right? Again, that's one of the main weaknesses of this book is that it has its problems really partitioned topic by topic and even subtopics, so it doesn't give you as much sort of, I don't know, open exercises that are not bound to sections so you can learn which technique you should use. Now, okay, so you wanted an example with higher powers. So I aim to please. Example 6 here. How about the integral of dx over x squared plus 4x plus 5 quantity squared. Now this one, at first glance, you're like, I thought you just told us that trig substitutions for removing radicals. Yes, true, but also these. Okay, so if there's a sum of squares in the denominator, and because if you can make the denominator into a single thing squared, algebraically that's much easier to handle. Sum of squares you can't break up, right? This is not an algebraic step. It's no allowed, right? This is not, no. Sorry, there. I mean, handwriting aside, this is no bueno. No. No can do. This, on the other hand, what you do is you go, okay, so this is dx over x plus 2 quantity squared, right? Plus 1. Complete the square. Now we're in business. Now it's one of our generic sort of patterns. It's a variable squared, a variable term squared plus a constant squared, right? So, oh, I'm sorry. Can I try to make this into a, I haven't done a secant substitution yet. I'm trying to do I wanted to work a secant substitution today. Let me change this so it becomes a secant substitution. What would I have to do? I need it to look like what? To do a secant substitution, I need something like x squared minus 1. So if instead of having plus 5 here, plus 3, we'll do it? Perfect, thank you. So that makes this a minus 1. This freedom is only allowed to me. When you teach Calculus 2, you're also allowed to make such modifications. Okay? Just saying. It's been a long day. I forgot. Today's Monday, right? Oh, okay. Feels like Monday, though. Okay. All right, now, secant. We're in secant's house. So what you want to do is want to let x plus 2 equal to, and I got a 1 here, so there's no kind of funny multiplier. Just secant theta, just a plain old secant theta ought to do it. And that will be, so like x plus 2 squared minus 1 is going to give me a tangent squared theta, right? And my dx is going to give me secant theta tangent theta d theta. So what we got here, secant theta tangent theta d theta divided by, whoa, oh, I may regret doing this, tangent squared theta squared, right? Uh-oh. Now, because of the party day, our discussion of trig integrals got cut a little bit short, right? The good news is they came back. So here's an example we haven't touched on yet. Like, how do you integrate something like this? I don't think we've talked about this much, but how do you do it, you know? We got what? We got secant theta d theta divided by tangent to the what? Yeah, maybe I should keep a tangent up there for just a second. I'll tell you, I'll keep that tangent up there, but you said tangent to the 4th theta. I kind of like that. The reason I like that, ow, it's still there. All right, hey, you monster. Who laughed at that? Like my children. Let's see here. Tangent squared, how is that related to secant squared? Tangent squared theta is what? Was it? It was
Secant squared theta minus 1.
secant squared theta minus 1. All right, I'm not sure that I'm going to a good place here, but I'm going to try something. So this is, ooh, yeah, I don't know if I like where I'm going. I'm going to go there, though. I don't know if it's a place we can get back from at the moment. But this is secant squared theta minus 1 squared. So yeah, that's apparently du over u squared minus 1 squared. I have now turned the integral back into an integral of the same type, but cleaned up a little bit. You don't have to write this stuff down. It's not helpful. I mean, you can write it down as a lesson of what not to do if you want, but so this has not been productive. What should we try? I'm gonna, go back up to here. Try something a little bit different. It's not helping. Sometimes when I have something like this, if I'm stuck, I will convert to sines and cosines. So this is really what? 1 over cosine theta, and that's sine cubed theta over cosine cubed theta, right? That's the net tangents. I got tangent cubed downstairs, so the sine cosine content of that is sine cubed over cosine cubed, but denominator or the denominator is really the numerator. May or may not be helpful. I don't know. What we got here? Cosine squared theta divided by sine cubed theta, yeah? Yeah. Uh-huh. Huh. Yeah. Well, I mean, it would be so lovely if that was just a cosine d theta, If that was just cosine theta d theta, we'd be home free. But that extra cosine, it's cramping my style. Well, I wasn't intending this as an example of a hyperbolic substitution, but let's try. What happens if we try to do this one hyperbolically? What would the hyperbolic substitution be here? If I had left it as a tangent type integral, it's actually pretty easy. I'm an idiot. I made my easy example into a hard example. Okay, so what hyperbolic function should I use to, change the difference of squares downstairs into just a single square? Cos squared, let's see here, so this would say what? This says that cos squared theta minus 1 equals to sinh squared theta, right? So this suggests that if I have the pattern variable squared minus 1, a hyperbolic cosine substitution may be useful. So what I'll do is I'll say x plus 2 is cos phi, well, cos theta. Because then x plus 2 squared minus 1 is what? It is sinh squared phi, right? So this is the integral of, and it may not be any better, guys. There are some problems that are just intrinsically difficult. Whether you look at them hyperbolically or look at them trigonometrically, either way, they just, hurt your brain. This is going to give me sinh theta, but I think I'm kind of liking where this is going. Right, because x plus 2 squared minus 1 is sinh squared theta. Right? And the derivative of cos is sinh. Oh, so that's what? Ooh. Yeah. Ouch. That's sinh cubed downstairs, isn't it?
Substitute.
I mean, I can do it. I'm pretty sure, but this is... yeah. This is a nasty integral is what this is. So my attempt to give you a higher power one has gone sideways. I should have just looked in the book and picked one.
I appreciate it.
But, okay, guys, so, our time is pretty much up for today. But let me just tell you the big story here. There are, in fact, substitutions that will take any rational, basically any rational function, and convert it to a rational function in sine and cosine, which you can then integrate. I mean, pretty much this bag of tricks will allow you to integrate most rational functions. It's just a matter of persistence. I'm not saying that we can't do this integral. I'm just saying that I'm tired and I can't do it at the moment. Right? I just made this example up, so I didn't know where it was going to go. And we went down an alley and I got mugged. So, I guess I'll say you. So, and then this guy also was waiting. So, I mean, sometimes you do a hyperbolic substitution, it's like, oh, okay, well, I can do that. But this one, not so much. It's about as bad as that. Oh. So, I mean, this is still not pleasant, but this actually works out to cosecant cubed theta minus cosecant theta d theta. Both of those, this, you can do by integration by parts. It loops. This cosecant theta integral is something similar to the secant plus tangent integral. So it's unpleasant, but that's a path forward. Yeah. Anyway, somebody had a question before I interrupted. Oh, you're going to do that? Oh, okay, cool.
I mean, I went about it kind of a different way.
Did you get the answer to the end?
No.
Not yet.
I just separated the...
Yeah. But I have a bunch more examples. Anyway, I'll try to go over some more examples of this tomorrow. I think we should spend another little bit of time on this. Yeah.